Hi everyone, this is Prime SD, Prime Senior Design. We're working on bridge number 03641 in Milford, Connecticut. And I'm going to introduce all our team members. So my name is Matt.
My name is Fu.
My name is Jacob.
My name is Frank.
So Prime SD consists of the four members you just met: Franklin Vasquez, Matthew Wenlin, Jacob Vidiera, and Fu Tan. Also, this project would not be possible without our sponsor, Brian Chamberlain. Bridge 03641 supports Naugatuck Avenue over Metro North Railroad in Milford, Connecticut, consisting of two spans, which total a length of 99 feet. However, the project focus will be on span 1 of the bridge. According to a fracture critical and routine inspection taken in January 2021 of Bridge 03641, the existing superstructure is considered to be in poor condition, primarily due to deteriorated steel stringers. However, existing floor beams and girders are considered to be in fair condition, and the existing substructure is in satisfactory condition.
The proposed solution to the rehabilitation of Bridge 03641 includes two major sections: the repairs to the superstructure and other minor items. The other minor items do not gain the full attention in this project as they are mostly industry standards. Stringer Design and Analysis by Matthew Wenlin and Franklin Vasquez.
A large portion of this project revolves around repairing and replacing certain portions of the steel superstructure. Over time, these steel members experience damage due to weathering and rust, resulting in several areas of section and webbing loss, as shown. Part of our response to this is to repair and repaint the damaged floor beams and girders as needed. Additionally, the damaged stringers will be replaced with stronger 50K size steel members. The capacity of these members and the bolted connections are verified through manual calculation and through software modeling. With these measures, we extend the lifetime of the superstructure and increase its load-bearing capacity.
The design of the steel members of Bridge 03641 were drafted in MicroStation. The framing plan is shown. The load path is as follows. The live load is applied to the concrete deck, which is supported by the steel stringers which run parallel to Naugatuck Avenue. That load from the stringers is then transferred to the floor beams which run perpendicular to the road. That load is then applied and transferred to the end girders which run parallel to Naugatuck Avenue. Girders then transfer the load to the substructure, which consists of the two abutments and the one pier. The design vehicle used for calculating the demand of the stringers is the HS-20 design truck. The diagram shown includes the loads applied by each axle. To analyze the stringers, the demand was applied to the stringers in SAP 2000. The loads considered include the dead load and the live load. To compute the live load, we considered factors such as the dynamic factor and the distribution factor. The demand was found to equal 55.179 kips. Table 7.1 in the Steel Design Manual, along with some manual calculations, were used to find the capacity of the stringers at the connections. The connections consist of 4 A325 bolts. The capacity of the 4 bolts was found to equal 97.36 kips. This means that the capacity is greater than the demand, and therefore the structure can withstand the applied load.
Deck Design and Analysis by Jacob Vidiera and Fu Tan. The team decided that using SP slab would be the most appropriate tool for the deck design, as it is a concrete deck. Here we can see a bunch of information solved for from SP slab that will be used for the bearing capacity calculations later down the line. For the analysis of the applied loads, we see that a giant applied load is spent over the entirety of the deck, which makes sense as it is a very long deck. For the deck analysis, we can also see that number 5 and 6 bars must be used to reinforce the deck so it doesn't collapse. For the deck analysis of the fence, we see that a 9-foot vertical fence is needed to comply with CTDOT BDM codes. For the deck analysis fence calculations, we see that it is preferable to use tension bars 4 feet apart from one another to reduce the amount of wind loads applied to either side.
Hi, this is Futan. So my part of our bridge is the design of bearings, and I'm focused on the design of reinforced elastomeric bearings. And the first is about the influence of low temperature zones and the minimum grease of the elastomer. Secondly, I'm doing the calculation about the design of bearings, and first I calculate the total height of the bearing HRT. Another one is a share key between the band cap and the console diaphragm.
What should also be mentioned is that minor repairs need to be made over the substructure of the project, as well as repairs to the railroad shielding that will be used during the construction process, a new fiberglass sidewalk, and a full cost estimation that is developed that you can see in the bottom right hand corner. Thank you very much to the Prime SD team, Professor Wei Zhang, Brian Chamberlain, the Department of Civil and Environmental Engineering, and to all the judges viewing this video.